Welcome back to part 2 of our 5-part series. Last time we covered the global temperature record. Today, why isn't the whole planet heating up evenly? And why is the Arctic changing so much faster than everywhere else? Since 1979, the Arctic has warmed nearly 4 times faster than the global average. That's not a typo, 4 times faster than the rest of the planet combined. NOAA's latest Arctic report card found the region just had its hottest year in 125 years, with winter sea ice hitting its lowest maximum extent in 47 years of satellite record-keeping. So what's actually driving this imbalance? Let's break it down, mechanism by mechanism. This phenomenon is called polar amplification, or Arctic amplification, and it isn't just about the Arctic being warmer. It's about the Arctic responding to the same global forces in a completely different way. This isn't one team's finding. The nearly 4 times ratio holds up independently in both NASA's temperature record at 3.9 times and the UK Met Office's record at 4.1 times. This ratio wasn't always this high. Arctic amplification has intensified significantly over just the last 2 decades, tracking closely with accelerating sea ice loss. One honest caveat before we go further. Scientists agree the pattern itself is real and consistent, but the exact weighting of each mechanism driving it is still an active area of research. Let's start with the mechanism. Most scientists consider the primary driver: ice albedo feedback. Bright ice and snow reflect sunlight back into space, a property called albedo. Fresh snow and ice can reflect up to 90% of incoming sunlight. As that ice melts, it exposes darker ocean water underneath. Darker water absorbs far more solar energy instead of reflecting it, which accelerates further melting. Here's a detail most people miss. Arctic amplification is actually strongest in autumn, as the ocean releases the extra heat it soaked up all summer long back into the atmosphere. Traditionally, ice albedo feedback has been considered the single biggest contributor to Arctic amplification. Though, as we'll see next, it isn't acting alone. And critically, it compounds every single melt season. Less ice this year means more heat absorbed, which means less ice forms next winter, and the cycle deepens. The second mechanism is about heat that doesn't originate in the Arctic at all. It's transported there. Narrow, dense bands of water vapor called atmospheric rivers drag warmth from the tropics all the way north into the Arctic, injecting heat that didn't form there locally. Newer research suggests this remote heat transport through both the ocean and atmosphere may be just as important as ice albedo feedback. A bigger piece of the puzzle than scientists once assumed. The warming is significantly stronger specifically above the Arctic Circle, at 66.5 degrees north, and it varies notably depending on season and exact geography. Climate models still struggle with this piece. Researchers openly acknowledge that current models tend to underestimate just how strong these heat transport mechanisms really are. And it doesn't stop with ice and heat transport. There's a third mechanism building underneath the surface, literally. Permafrost stores roughly 1,500 billion tons of organic carbon. That's about twice as much carbon as currently exists in Earth's entire atmosphere. As permafrost thaws, microbes decompose organic matter that's been frozen for thousands of years, releasing both carbon dioxide and methane, which fuels even more warming. It's a feedback loop of its own. The scale of the risk depends heavily on how hot it gets. Up to 50% of near-surface permafrost could thaw at 1.5 to 2 degrees of warming. At 3 to 5 degrees, that rises to up to 90%. Researchers estimate roughly 100 gigatons of carbon dioxide may need to be subtracted from the entire global carbon budget, just to account for this one feedback loop. So here's why all of this matters even if you live nowhere near the Arctic. It may already be shaping the winters where you live. Rapid Arctic warming is linked to a wavier, weaker jet stream. As the temperature difference between the Arctic and the tropics shrinks, the jet stream that normally contains cold air can weaken and buckle. When the stratospheric polar vortex weakens or splits apart, the cold Arctic air it normally contains can spill much further south than usual, straight into the mid-latitudes. This actually happened in January 2026. A sudden stratospheric warming event disrupted the polar vortex, contributing to a major cold wave that swept across North America. Another honest caveat: scientists still actively debate exactly how strong this Arctic to jet stream connection really is. It's an evolving research area, not a fully settled consensus. So paradoxically, a warming Arctic can still produce brutal, disruptive cold snaps thousands of miles south. That's not a contradiction. It's the same disrupted system producing both effects at once. Zoom out, and the Arctic starts to look like a preview of the rest of the planet's future. Because it's changing fastest, the Arctic reveals feedback loops and consequences before they become visible anywhere else, showing us in years what may take the rest of the planet decades. Some research suggests the amplification ratio itself may have already peaked in the early 2000s, tracking the fastest years of sea ice loss. But the Arctic still remains far above the global average today. None of these mechanisms work in isolation. Ice albedo feedback, remote heat transport, and permafrost carbon release all combine and reinforce each other simultaneously. Which brings up an obvious question. If polar regions amplify warming, why isn't Antarctica behaving the same way as the Arctic? Geography flips the whole picture. The Arctic is essentially an ocean enclosed by continents. Antarctica is the reverse, a continent enclosed by ocean. That single difference changes everything. A powerful ring of wind and water, called the Antarctic Circumpolar Current, circles the continent completely uninterrupted by land, acting like a shield that isolates it from warm air and water intrusions the Arctic doesn't have. So Antarctica isn't immune, it's just slower and more mixed. The deep interior shows a genuinely uncertain trend, while West Antarctica and the Antarctic Peninsula are already warming and losing ice rapidly. Which raises another question we haven't answered yet. If melting ice can change ocean currents and the jet stream, can it also destabilize the ground itself? Melting ice doesn't just change temperature and ocean currents. It changes the actual physical weight pressing down on Earth's crust. And that has consequences we're covering next. That's exactly what Part 3 covers. The real peer-reviewed science linking melting glaciers to earthquakes. Let's pull it all together. Nearly 4 times faster. How much quicker the Arctic warms compared to the rest of the planet. The hottest Arctic year in 125 years, with winter sea ice at its lowest maximum in 47 years of satellite records. 3 mechanisms, all compounding at once: ice albedo feedback, remote heat transport, and permafrost carbon release. As always, a new video every 5 days. Part 3, The Ground is Talking. The real peer-reviewed science linking melting glaciers to earthquakes. Thanks for watching this deep dive into why the Arctic is changing faster than anywhere else. Subscribe so you don't miss Part 3, out in 5 days, and drop your questions in the comments below.